Today we're going to take a look at section 2.2, which is measures of change at a point. This is the one we're on, right? Yes, that's fantastic. Okay, there's one change when you get to the end of your notes that I made this morning or last night online. So if you've printed them out recently, they're on your printout. If you haven't, if you printed them out earlier, it references a specific page in your book. So I'll make mention of it when we get there. All right, so instantaneous rate of change. I mentioned last time we were going to come across one more rate of change, and that it would be called IROC. This is instantaneous rate of change. The instantaneous rate of change is the slope of a curve at a point. And this is the time when we're not going to say past tense ed. It wasn't increased or decreased. It will be increasing or decreasing. So here's the difference. Okay? When you are driving your car or riding your bike or running on a treadmill, somewhere on some screen somewhere, it tells you how fast you're going right now. That's your instantaneous rate. Okay? Now, if you calculate at the very end of your run on the treadmill or at the very end of your driving to and from work, how long it took and how far you went and all of that, that's your average rate of change or your average speed. Okay, that's the difference. So we're looking at the instantaneous rate of change today. Local linearity says that if we look closely enough at any point on a smooth curve, the curve will look like a line. The line is actually called the tangent line at that point. And you've probably all had the experience in your calculator at some point that it wasn't in a very good viewing window, right? You needed to zoom out or zoom in because it didn't quite look like what you were expecting. You looked at the equation, you said, yes, it's a parabola, and you looked at your screen and you said, that looks like a line. That's local linearity. If you look close enough at a particular point on a graph, it will look like a line. And that line is called the tangent line. There are only two places where tangent lines actually cut through a curve. One is at an inflection point. Remember, inflection point is when you change concavity. And the second one is if you actually have a line to start with. So if you have a line to start with, then the slope of that line is, in fact, the slope you're talking about. It's the line itself. All right, so we need to do an example. So if you have something that's a straight edge, maybe you've got the edge of your calculator lid or your ID card or another sheet of paper, grab something out that can serve sort of as a straight edge like a ruler, okay? Anything flat will do. ID cards are great because they're strong enough to keep you straight without being bulky enough to take up a lot of space. Okay, but grab folder will work. Yep, that's fine. Okay, so what we're going to do is we're going to line up the card or the whatever you're doing so that when it crosses the point, yellow will work. When it crosses the point, it looks like it's barely touching that point. Okay? So it wouldn't be like this because that would be eventually sort of cutting through the curve. It needs to be barely touching the curve. And that is what we're calling, I'm giving the name to, as the tangent line. So I'm going to draw one on my screen. And we're going to do it at each of these points so we can see what they look like. All right. That's pretty reasonable. Okay? The idea being that if I tilted the line in either direction, it wouldn't be quite as close as it is right now to both sides of the curve. So this is the value at point A, or the tangent line at point A. What do you notice about point B? What kind of a point does it appear to be?
An inflection.
It looks like an inflection point. And over here, this is one of the things that I told you, is that if it's an inflection point, we actually are going to cross through the curve, right? So how does that look? Because like this is not what I mean. That's not a tangent line. It crosses the curve, but it is not a tangent line. The tangent line needs to hug the curve, be very, very close to the curve on both sides of the curve. Sorry while I draw this because it's easier to draw it than move it. So if you take a look at this, very, very slightly on the top of B, it's crossing above the curve, and very, very slightly below B, it's crossing below the curve. Make sense? That would be the tangent line at point B. What do you suppose the tangent line would look like at C? What is this called, Luke? Horizontal. You're right. It will be a horizontal line at C. Okay? There's no way if I tilt this in either direction, whoops, If I tilt this line in either direction, it moves it further away from the other side. So this is as close as this line will get to both sides of the curve at the same time. And we'll skip it for a second, go up to E. E will be the same, right? So anytime we have the peak or the valley of a curve, it's going to be a horizontal tangent line, which will be important information for us later on. So this one up here looks like this too. Right? And then the last one at point D, we'll draw that one in. Looks something like this. So these are the tangent lines that it talks about. Now going back to the directions of the question, it says we're going to decide if the slope, or the instantaneous rate of change is another way of putting it, if the slope or the instantaneous rate of change is positive, negative, or 0 for each one of these lines. So we're just going to make a list. At point A, is the slope positive, negative, or 0? It's positive. At point B, is the slope positive, negative, or 0?
Negative.
It's negative, right. What about C? That one's 0. The slope is 0 for horizontal lines. D? Positive. And E? 0. And if you had to, you could actually even put them sort of in order from smallest to largest, right? I mean, obviously the zeros are there in the middle, but a negative slope for B would be the most, or the smallest slope, right, in a negative sense. And then if you compared A and D together, it looks like D is a bit steeper than A, right? So D is a bigger value or a steeper slope. So it's the largest one on the graph. If you needed to put them in order, you could do that. Any questions about the tangent line images right now? All right. So we're going to actually find an approximation for a tangent line's slope value, like the actual slope. Yes? D was the steepest. Say again?
Wouldn't the slope be smaller if it's steeper?
If the slope is steeper and it's positive, it's bigger. So like imagine, we're just pretending numbers, but imagine this one was steeper, so it would rise up to and over 1 maybe, and this one over here would rise up 1 and over 1. That's what that would look like, so you get a bigger value. All right, so I'd like for you to create a tangent line through this point. So I think we're on page 2, it looks like, maybe. And after you've created your tangent line, we're going to approximate what the slope is by choosing 2 points on a straight line and calculating slope. Okay? So go ahead and see what you get. And after you've calculated the slope, I want you to compare with a neighbor. But as you do this, recognize your answers are going to differ probably a little bit. And that's okay. So you're going to draw a tangent line, and you're going to select 2 points on the line. So your tangent line should look like it cuts through this one. Why? Because it looks like an inflection point, yeah. So the longer you draw your tangent line, the easier that it's going to be to make the calculation, because you'll have more options for choosing points. You can pick any 2 points on the line that you've drawn. What point might be nice and easiest to pick? The point itself would be a good one to pick, right? That would be the same for everybody. Agreed? What would another point here be nice to pick after you've drawn it? Oh, somebody said it. Where it intersects. Which one? The x-axis is on my picture, right? So it might be useful to pick this particular point here and this one. Do you have to pick those points? No, you don't. You can pick anything. So whichever one seems to be easiest to see to yourself right now, that's what you would pick. So this one looks like, they're not marked, but if they were, this would be 3.5 on the x. And it looks like 4 on y. Okay, so I think all of us will have the point 3.54. Your x-intercept might not quite look like mine, right? It might be a little off from what I have. That's okay. So find yourself 2 points, calculate the slope, and check with the neighbor. What kinds of slope values did we get? Negative, okay, good. What answer? So tell me your answer you had. Dakota, I can just tell you want to say something. What'd you get? Negative 1.6. Did anybody else get exactly negative 1.6? Okay, you did, Kendra, right? Okay, good. What else did we get besides negative 1.6?
2. Negative 2.
Negative 2, okay. Anything else?
Negative 1.739.
Negative 1.739. Okay, so let me ask you this question. Are all of these numbers pretty close together? Yes. Yes. So if I got something in this ballpark, I'd be okay, right? Yeah. What if I got negative 3? Probably not okay at that point, right? What if I got negative 1.1? Probably not okay. Okay? There are answers that would be correct, and then there are some that are far enough off that obviously they're not. So let's see. Hannah, you said you had what I had. So I used the point down here, 5.8. So mine would actually be 5.8. Whoops, that's the x value, not the y value. My apologies. 0 for my y value minus 4. And then 5.8 minus 3.5. And Hannah, you told me that was what?
Negative 1.739.
0.739. Okay? And if you do end up with decimals, of course, we'll use 3 decimal places on this just like we have been. Okay? So your answer should be somewhere around that value. Okay? Any questions? You guys have been finding slopes for ages, yeah? Yeah, like probably 6th or 7th grade. Okay? Fabulous. So it's no different than before. Oh, percentage rate of change. This would be where it would be nice to have my notes, wouldn't it? All right. I think I can remember what I want to say, though. All right? Your percentage rate of change at a point. Now, we've had something before that's actually called a percent rate of change. So the phrasing here adds what to it? What changed in terms of the label that I'm giving this? It's at a certain point, but what else in terms of the words used at the beginning? It says percentage instead of just percent, right? Yeah, so it won't be a huge issue. I just want you to recognize that they do actually call it something slightly different in your book, okay? So don't freak out on me and be like, oh my goodness, I have to look for the word age. And if it's there, I do this, and if it's not, I do that. You'll know, because they'll only give you 1 point, and then you're going to do this. And if they give you the other one, they'll give you 2 points. That's how complicated that is, okay? So 1 point, this is what you do. So here's what you do. You calculate. Well, actually, you know what? Let me put this down here first to remind us. You tell me, what did we have for percent change? F of B. Mm-hmm.
F of A over F of A times 100.
Good. That's what that looked like for percent change. All right, so then for percentage change, what changes? Well, the denominator stays the same. It's still f of a, and the times 100 stays the same. That's all cool. What changes is the numerator. And this is the first time I've used this notation, so let me write it down. And those of you who have calculus, just bite your tongue for a second while I actually say what it is at the moment. Okay? Y'all good with that? Some of you are already biting your tongue. I can see it. All right, what goes on top is f prime of a. And I need to tell you what f prime of a is. F prime of a is the slope of the tangent line at A. And we'll have another name for it when I start 2.3. Okay. But this is what it is. It's that slope that we just calculated. So right here, we could actually say right here that f prime of 3.5, because this is the location where I drew my tangent line, is negative 1.739. At least it was on my screen. This is the value. Okay? It's the slope of the tangent line. All right, so here's the one that I've actually included the picture of from your book. It's page 150 something. Somebody have the old printout? What's it say? 151, number 25. So if you want to, you can grab your book to get this image. If you've already got it printed out on paper, that's fantastic. We're going to take a look at this, and it says, the figure shows the total number of cellular phone subscribers in the United States from 2000 to 2008. First one says, draw a tangent line to the graph at P and estimate the slope. Okay? So let's draw a tangent line. Either flip your book open and sketch it inside of your book if you want to, or if you've got it already printed out, we'll do it on here. It will be easiest, just like we did on the last one, if you can make your line longer so that you have more options to see the points where it would have on the line. All right, I'm okay with that one, I guess. Okay, so let's all do the points that we're using together on this one. What does it look like as the point P, x value, y value first? 5 and 62.5 sounds fantastic. Okay? And then I'm kind of a big fan of looking at where it crosses axes because it sort of simplifies one of the two variables. Like I look at that one and I see the x value, or at least can approximate the x value easily. Where does it look like it's crossing the x-axis? This is an approximate, so we might as well use 1, right? It looks like it's pretty close to 1. Agreed? So the point that I'm looking at is down here. So this is crossing at the x value of 1. What's the y value there?
45.
It's actually 45, isn't it? So be careful. Just because it's the axis doesn't mean it's 0. You have to look over at the axis key on the side. The scale. It's 45. All right, so these are our 2 points that we're going to use. And we are going to calculate the slope, because that's what it told us to do. So to calculate the slope, what we're actually finding, just as a clarity, what was this called? It didn't give us a name, so I'll call it f. We're actually finding f prime of P, the x value, which is 5. All right, so calculating slope. I do y2 minus y1. So which one do you want to do first, 45 or 62.5?
60.
All right, 62.5 minus 45. 62.5 goes along with the x value of 5. 45 goes along with the x value of 1. What is 62.5 minus 45, and then divide by 4? 4.375. And we have units, so we're going to write them down. What are the units for this particular slope? 100,000. That's part of it.
Per year.
Good. 100,000 per year. So in terms of a graph, if you remember, it's always output per input. 100,000 per year. That's the tangent line. The second one said, what are the units of measure for the slope of the tangent line? Oh, yay, we already did that. What are they? 100,000 per year. So we'll write that in here. And then it also asks us to give a sentence of interpretation. So we haven't done a sentence of interpretation for one of these yet. So let me show you how that looks. Remember last time we had 4 things to write down anytime something was changing. What was the first thing? Yeah, I think we called it when, right? The location and time of whatever is happening. So the when right now is not over a span of interval, right? It's not a time interval. It's at a specific point in time. In particular, what is the specific point in time of this particular point? It's 2005, because this is year since 2000, and we're at the p-value of 5. So we're going to say in 2005, not between anything, because this is at a specific point in time. In 2005. So when was the first thing? What came next? This is like, the party invitations, who, what, when, where, why, and how kind of stuff, right? When, and then what? What's changing? What did it say over here? Yeah, the cell phone subscribers in the United States, right? So that's what we're going to write down in 2005. The number of cell phone subscribers in the U.S. Okay, so we have the when and we have the what. What came next? When, what? Man, it's been 5 days, right? It's a really long time. I called it how. How, and the how has to do whether it was an increased or a decreased.
Increased by 62.
Okay, so you said increased. So why is it increased? Because the slope's positive, right? So this is increasing, right? We talked about that at the beginning. We changed that language because it's happening at a specific point in time. It is currently, at that point in time, doing it. So we had, let's see, the U.S. is increasing by, and then you wanted to finish out for me. And then it's the by how much. So what were you going to finish out for me?
62.5 100,000.
See over here. Nope. The slope that we found. So what did we find for our slope, Brooke? Yeah, it's the 4.375 that we're going to put next. So let me erase this piece. Increasing by 4.375.
100,000 per year.
Good, 100,000 per year. Okay, this is a lot like the ones we just did. The only thing that changed was that we have a one date on there. This was dates. So we have the 2005. It's not an interval of time. And we have that ing, present tense, and not the past tense of ed on the word increase. Increasing, not increased. Okay, I think there's one more question. Ooh, calculate and interpret the percentage rate of change at point P. Okay, so I gave you a formula a minute ago for percentage rate of change, and it looked something like this. F prime of A over F of A times 100. Right? Move this over a little bit. Okay, so the F prime of A, that's actually what we calculated over here. Whoops, one more back. We calculated the F prime, okay? And we know what the F of A is as well because we used it to calculate the F prime. So we should be finding F prime of 5 over F of 5 because these are the input values at point P for X times 100. So F prime of 5 was 4.375, is that right? Okay, good. What was F of 5? That was my 62.5. And then we need to do times 100. What will we get? 7. Even? Exactly? Wow. 7 what? And it's actually percent per year. So let me explain that, because that is different. When we calculated percentages before, they were just percent, right? And the kicker is that this 4.375 on top, what were the units on 4.375? This was 100, and I'm running into the white, so I can't get it in there. This should be 100,000 per year. I can hardly write it, but it's there. What are the units on the 62.5? 100,000. So what cancels? The 100,000, and what's left? The per year gets left, right? Because it's a rate of change on top, and it's an output value on bottom. So the 100,000 per year has the per year left. The percent is because I multiplied by the 100%. So that's where the percent came from. And the per year is because that's what's left from my numerator. Now, we need to do an interpretation, and then we're finished with this one. It says we're supposed to interpret the percentage rate of change at point P. So, interpretations, when, what, how, and by how much. Always the same. So what's the when in 2005? Whoops, let me use the white. In 2005, what's the what? Yeah, it's the same as the last one, right? So far the same. So the number of cell phone subscribers in the U.S., that's the what. What's the how? Increasing or decreasing, and this one is increasing. So it is increasing, present tense. It is for the percentage rate of change. Yes. It is for the instantaneous rate of change. And it's also associated with only having one input value, right? The fact that this is happening in one specific year instead of over a time interval. Okay, is increasing, and then how? By 7% per year. Good job. Very well done. Any questions on that? All right.